f of x, define an fp to fp. What was p usually for our project? If you've been doing the project. 79, right? That's so far we had been playing with the 79 characters and letters, and here's x to the a. All right. What was the last example, Sage example, that involves this type of thing? A was 47, was it not? Yeah, 47. You raise everything to 47. Turns out it's a bijective function. So today we look a little bit more closely to when is it bijective and when is it not, that kind of things. So given by the function like this, it's sometimes not bijective, right? Not bijective. So here's a big theorem that Fp can be generated by this type of element, G0 and G1, all the way up to G to the what power? Let's play one more time. P minus 2, right? What happened to the P minus 1? Going back to the 1, right? What is that theorem? Fermat's theorem. Everything raised to P minus first power, then it's going back to 1 if it is non-zero element in fact. So we have that, and well, we start from 2. See if the 2 works and 3 works, and it guarantees it is a field, and then there will be something that works, right? But it could be 2, maybe 3 works as well, and there are many other elements, okay? So how many elements are there? That's a different question, but don't think that G is unique there. 2 might work and 3 might work as well, right? So we can just grab one that is convenient for us. So there are many choices of G. From there, that's the statement of theorem, that always there. From there, we can define this log G, right? Log G. How do you calculate log G of x? First, you have to write x in terms of power of G, right? That's the, if I give you 35, when P is a 79, you have to realize it as a power of 2. Actually, 3 worked. 79, I remember. The 2 is not a generator. 3 is a generator. So you have to write, if your choice of G is 3, you have to write given number, 35 whatever, as a power of G. Okay? Why is it always possible? If I give you a number in between 0 and 78, between 0 and 78, you can, how can you always write it as a power of 3? It's a silly question. I said that everything is a power of, that's the theorem, right? Everything is a power of G. That's what this theorem is saying. So if you have an element, you can write it as a power of C. Whether we can do this uniquely or not is an easy thing to prove, but I'm not going into it. So there's a unique number between 0 and P minus 2 that does it. So what is the value of this one? Log G of G to the K is a K, right? What kind of theorem is that? It's a trick question. What kind of theorem allows you to log G of G to the K becomes a K? This is definition. This is not a theorem, right? There's no logarithm. These are not real numbers, so we're defining it like this. And there's a unique K in between 0 and P minus 2, therefore that's our definition. Okay? This is discrete logarithm. If you choose different G, and then it's a different map, just like the real numbers. Is that right? Next thing I want to emphasize is this diagram. And if you understand this commutative diagram, that's a great success. That's the main goal of today's lecture. All right. So here is something called commutative diagram. Commutative diagram. I will use an example, but first it's a some general picture. So we have Fp here. I forgot to emphasize it here. I'm going back to log functions. So log G, so what is the domain of log G? Anybody remember log G domain? Was Fp star, right? Fp star. And it lands in how many elements? P minus 1 elements, right? What is that world? What is the codomain? with a z p minus 1. Okay? Because multiplicative, the way the multiplicative works, what happens to exponent is it additively works, right? So that's why it's like that. Not only you match the number of elements, there's p minus 1 element in fp star, and there's z mod p minus 1, there's p minus 1 element. Not only that, it kind of reflects, here's a multiplicatively they're interacting, and here's additively they're interacting. That's what's emphasized. Okay, so I think I decided to do horizontally here. So that's fp. So about this, I'm going to change it to this connection, log map, log g. Under log g, we go to f of p minus 1. Okay? So that map we just talked about, we're going from fp star, sorry about this, fp star, to z modulo p minus 1. Is that good? That's that map. And we have fp to fp star given by f of x raised to x raised to, here I'm using this a, so x to the a. Okay? I already told you that if you choose a bad a there, it may not be bijective. But first I want you to understand this map from fp star to fp star is well defined in here. If you raise a non-zero element to a higher power, do you think you end up a non-zero element? Two, in case of 2, sitting inside z mod 4, if you raise the 2 to a second power, what happened? 2 into z mod 4. If you raise to the second power, does that become 0? It becomes 0, right? But I'm saying here it doesn't happen. No matter what you plug in here, if you choose a non-zero element, if you raise it to the higher power, then it's going to be non-zero. And if you choose like 3 here, no matter what power you raise it, you know it's not going to be 0, right? Because it's relatively prime. So let's first understand, if you choose a number that is relatively prime to p, then if you raise any power, it's going to remain relatively prime to p. Right? It's not going to pick up any extra factor. So we still have this map here. What is this map? Is this log g. Okay? So there are 3 maps, but 2 of them are same map. Okay? So think about it here. This is the commutativity. If you started here, if you have an element in fp star, an upper left corner, you go across the log g, and you can make the map in here, and then if you raise to 8th power, you landed in somewhere else in fp star, and then you do log g. So there's 2 ways to get from here to there. Okay? So from raising to 8th power and going in this way, and do the log g first, and do something else later. So that this map lands at exactly the same thing. So if I start with x here, I go down to the x to the a, right? And then whatever the log g, this is not g, so the map is not a. But no matter what the elements you have it here, there is a correct exponent for that g, so it's going to be some sort of k, whatever that is. And x is going over there, and I don't know what that is, so I'm going to call this m. So m is maybe not a good notation, but it's all right. X goes to m, that's the exponent, and m is mapped to k. And then if you go this way, that way, that way, that way, that doesn't matter. So there is this map h induced by this process. If I go find this exponent first, raise that to the 8th power, and then find the exponent later, and this is how the h is defined, so that it doesn't matter how you go about it. Okay, so this map is called HA. So HA is induced by that map FA, okay, along that logarithmic. So I first want you to write down this diagram and put a big question. I think he explained it, but I don't understand what this H map is. That's perfectly normal question. I think I understood everything except that part, right? HA, kind of vaguely defined. How about f of x, right? F of x is clear, right? Raise everything to the 8th power, and this is a logarithmic map. If you have these two maps, and it forces to create a map between z mod p minus 1 to the z mod p minus 1, such that doesn't matter how it travel, you end up with the same element. That property is called the commutativity. The commutativity defines that remaining map. So we're going to look at example, our part. So we're looking at example, p equals 11, looking at the function fp, star to fp star, raising to third power. And we're looking at log 2. Is that right? Because we're looking at 2 as a generator. Okay? So we have f11 here, star. How many elements are there in f11? So let me follow my instructions. So that's any questions so far before we do this first problem? Log 2. Yes, go ahead.
Back on the diagram.
Uh-huh.
What is f subscript a?
F subscript a. Sorry about that. This is f subscript a right there. Yeah. This raising to 8th power is supposed to be f sub a. That's notation. This goes with this ha. Right? Any other question? All right, first question is, I wrote here, is let's understand the function f in terms of the powers of 2 by not computing, but for using this example. For example, let's look at some examples here. f5 is 5 raised to the third power. Is that right? That's our f of x in here, because that's kind of, this is here, just abbreviated f3 here. That make sense? Good? So that's what f5 is. You can multiply this 5 3 times and reduce the mod 10. That's what this map is, right? What the map is. But 5 appeared here, that's a 0, 1, 2, 3, 4. So we can also write it 5 as a 2 raised to negative 0, 1, 2, 3, 4, fourth power. That's our 5 is, 2 to the 4th, according to this table in here, which is actually listed in correct order. Is that all right? So I'm trying to help you to understand this map, not in terms of this given number raised to third power, but in terms of the powers of 2. 5 is powers of 5. 5 is 2 to the 4th. So raising to the third power is really 2 to the 4th raising to the third power. Is that right? So basically, we have this 4 times 3. That's the map. All right, so whenever you reach the 2 to the 11, you know it's going to be 1, right? Remember, if I give you high power, you use Fermat's theorem to reduce that number. That's exactly the same thing we do. So how do we actually find out, not 12th power, but we want to figure out which one it lands in here, 0 to 10, right? So we can subtract multiples of something. What multiple can we subtract from this exponent? Using the Fermat's theorem. 2 to the, what is 1? 2 to the what power is 1 according to Fermat's theorem? 0 is 1, and what is the next number? P minus 1, 2 to the 10, right? Whenever you have 2 to the 10, it's going to be 1. So you can subtract of 10 to the whatever. Let's not use k. That seems like maybe L. How about that? Does that make sense? You know, 2 to the 4 times 3, that's there, but let's think about that remaining part. 2 to the 10 times L. 2 to the 10 is 1, right? So it doesn't matter what power you raise it, it's going to be the same. So that's what you did with the Fermat's theorem. If I have large power like 3,333, and how do you reduce this power? Is you subtract of the Fermat's theorem the copy, right? So 2 to the 10th, so that's exactly how much you subtract. So what would be the L so that you reduce this 4 times 3 nicely? Well, it's 1, right? So what is that result? 2 to the 2nd, is that right? 12 minus 10 is the 2nd. So you understand 2 to the 12th is the 2 to the 2nd. Right? So what this commutative diagram is trying to help you is that to see what happens to the level of this exponent. 11 was there. What is this horizontal map according to that in that horizontal, the commutative diagram? What was the label of this map? Horizontal map. Is that a log map? Right? Horizontal map was log. Log base what? Base 2. That's the map here, right? What is the vertical map, which is f here? X goes to what power in this context?
In the upper right corner should be F11 star B Z mod.
Oh, yeah, thank you. Yeah. This should be Z mod 10, right? This should be Z mod 10. P minus 1, right? Just to look at the exponent and just focus on what happened to the exponents. This is x to the third power. So that's the vertical map. All right? So what is this map again? Yeah. So log base 2. That's the map. And we want to understand what on earth is that map hx here, right? That's what we want to understand using this example. So each of them understand it's still difficult to understand what is happening to the h. So let's use this example 2 to the 4th there, right? So what happened 2 to the 4th? The 2 to the 4th going across it here, what elements does that become? Under log 2. Log 2 of 2 to the 4th? Let me write that down over here. Log 2 of 2 to the 4th. That's what I'm asking here. This is an element that we just looked at there, right? 2 to the 4th. This is an element there. And we started from there, not going across this F map, but we're doing this logarithm map. So that's what we're calculating. Log 2 of 2 to the 4th. What is that number here? This is 4, right? Log 2 of 2 to the 4th is 4. So it looks just like the real number log function, right? Does that make sense? All right. So that's the definition. Let's go back to definition of log g here. This is the definition. If you happen to write your input as a power of g, then log picks up that exponent, right? So that's what the log map is. A lot like a real number log map. So where does that go? 4 there, right? Good? Yeah. So what happened in terms of 2 to the 4th here mapped down to, so we are crossing it here and want to figure out what this side of the vertical map is. That should agree with just going around, detouring like this. So you're raising to a third power, that's the same as 2 to the 4 times 3, right? 2 to the 4 times 3. So if you happen to have this exponent here, and what will be the horizontal map? So that's what I'm asking. Log 2 of 2 to the 4 times 3, and what is that? It's 4 times 3 in the Z mod 10 world, right? So 4 times 3. Okay? So you start with the 2 to the 4th, which was really 5. The vertical, left-hand side of the vertical map raised to the third power. So what happened to the exponent is 4 times 3. So if you go to the horizontal map, which is logarithm map, of course it picks up 4 times 3, right? That's what this map is, right? But we are forcing this one as a commutative, so that 4 maps to what value? 4 maps to 4 times 3. 4 was an example that appeared as an exponent. This is where we started. Raising it to the power is the same as multiplying that exponent, 3 to that exponent. If you look at Z mod 10 world, what happened is that 4 was an input, and we end up at multiplying 3 to that input, right? So if I start with, in general, 2 to the, let's say, k, 2 to the k represent every element in F11 star. Is that right? Element. So what happened if you go through this map, vertical map? Raised to third power, isn't that just 3 times k? right? So if you go across this map, what happened? The exponents is a 3 times k, right? What happened if you go across this horizontal map? What happened to this value, to the k? Logarithmic map? It picks up just the k, right? And we want to map this k to where? Exactly to that one, so that it commutes. Doesn't matter which way you go around, you end up exactly the same element. So if I have hk, what would be the definition of hk? If I have k element in here, elements k must be 3 times k. So it's a 3 times k. It's all happening in what world? Z mod 10. Right? So the answer is simple. If you see x raised to the third power, what map are we talking about to this Z mod p minus 1? Multiplying that a to the Z mod 10. Because that's what's happening in the exponent. If you raise it, you multiply that to the exponent. That is captured in the second column. Does that make sense? All right. Suppose we have this general situation now. P minus what? P minus 2, right? Last one is P minus 2. And so I give you the generator, 2 or 3, whatever. So I want you to go and write down that. Also, I'm going to give you this function, fa, fp star to fp star, given by fax, given by x raised to the 8th power. That's the context, right? So I want you to put that commutative diagram, fp star in one corner, and fp star in the down there, and across it with the z mod something, you fill in, and you have this map fa in here, and dot, dot, dot. It's induced by all this other thing, that's HA. So I want you to go in and fill in, complete this diagram with these things in that each corner, and label each map. What is this map here? What is this map here? And what is this map to the right-hand side? You fill in that part so that it all commutes. No matter where you start, follow the arrow, and at the other corner, you end up at exactly the same element. That's the commutativity. All right? fax is already defined up here. So if you label it fax vertically like this, I think that does all. You have to fill in what is this horizontal map, and what is this vertical map, and what goes into this Z mod, this part. How was it? Was that okay? The vertical map is raising to the x8th power in the left-hand side. And what happened to the exponent level is actually multiplying that to the exponent. And under this log map, it just goes to the different world. So log g, or log base g, is the horizontal map. And h map is multiplying that a to the exponent. So that's that. So make sense? Commutative map? All right. So, and this log g is you believe that this side is a bijective? Would you believe that? Who can explain that log map is bijective? Yeah.
Is it because
I'm asking the horizontal map, which is the log map, right? Yeah. Why is the log map bijective? Maybe number of elements? Yeah, how many number of elements is the FP star? P minus 1, and how many elements are there? P minus 1, right? Why is that surjective? If I have k in there, how do you know there's an element that comes from here? G to the k, right? G to the k maps to G k there, right? So it's always surjective. So I don't think I did anything, and why does that really prove anything? It's because of the, well, definition of log g actually has a lot in it. So if you look, dig into the definition of log g, that itself proves that it's a bijective. So it's a bijective. So what happens here is exactly what happened. If you want to know if this is bijective, isn't that our question here, right? Bijective or not? That's our question, right? So bijectivity on that side, because of the bijectivity on the horizontal side, you can prove that if this map in here in the second column is bijective and this first column is bijective. So you come here, A is kind of arbitrarily given, and how do you determine this map A times X is a bijective? We did this problem already. It's the Z mod M world now. P minus 1 is no longer prime, right? So think about this map AX in Z mod M. That defines a function, multiplying A times to this Z mod M world. When is this bijective? So HA is bijective if and only if some necessary and sufficient condition on A, and it's a relationship between A and M, right? It's supposed to be 1. Because if this is bijective, it must be invertible. And why is it invertible? This coefficient must be invertible, right? When is coefficient A invertible in Z mod M? When A is relatively prime to M, right? That make sense? Okay. So this is the important thing. You have to box it. I bet you will be using this today. All right. Here, multiplicative world of a finite field looks really complicated. If you look at this number 2 and 10 and 7, you don't know what's going on. But if you go through the log map, what's really going on to the raising to a power map is really multiplying that power to this coefficient world, which is the same as Z mod P minus 1. All right? So let's look at this example. So did you write that down? If you have a linear map, not raising the power HA, it's a bijective map if that A is co-prime to, what is M here in this case? I forgot to write down what M is. M here is a P minus 1. That's our situation, right? So if A is relatively prime to P minus 1, and then it is. So let's go back to the exercise. Before, we had